You ever get that feeling that there's a secret code running the world, a hidden language that explains everything from the arc of a basketball to how your savings account grows? Well, there is. And today, we're going to crack that code. We're talking about functions, the fundamental rules that run our universe.
So, what in the world does a perfect three-pointer have in common with a booming savings account? I mean, on the surface, they seem like they're from different planets, right? But what if I told you they both follow the exact same secret rulebook?
Well, it turns out they both follow these incredibly predictable rules. You give them an input, like time, and you get a very specific, predictable output, like the ball's position or your bank balance. And in the language of math, we call these predictable rules functions.
Okay, to really wrap our heads around this, we're going to use a simple but super powerful idea. Let's think of a function as a machine. Seriously, this one metaphor is the key to unlocking how these things actually work. So what's the big deal about this machine? It has one simple, unbreakable rule. For every single input you put in, you get exactly one output. Not two, not zero, always one. It's this absolute reliability that makes functions the foundation for pretty much everything, from building a bridge to the app on your phone.
Let's see this rule in action. Over on the left, we've got our reliable, well-behaved function machine. You pop in a 2, you get a 3. Every single time. Predictable. But the machine on the right? Oh, it's a bit of a rebel. You put in a 4, and it might spit out a 2, or maybe a -2. That unpredictability? That's a deal breaker. It breaks the core rules, so it is not a function.
And this brings us to a brilliant little visual cheat code. It's called the vertical line test. If you can draw a straight vertical line anywhere on a graph and it hits the curve more than once, boom, you know you're looking at one of those rebellious machines. It's not a function. It's really that simple.
All right, so now we know how to spot a proper function machine. Next up, it's time to learn how to read its instruction manual. You see, every function has its own specs, what it can do, and what its limits are, and we're about to learn how to read them.
First up is the domain. This is basically just the complete list of all the possible ingredients you're allowed to put into the function. Some functions will take any number you can think of, but others are, well, they're a bit pickier. Like, you can't put a negative number into a square root function, right? It just breaks. So its domain tells you only positive numbers and 0, please. And if the domain is everything that can go in, you can probably guess what the range is. It's the complete set of every possible result the machine can spit out. It's the full catalog of everything it can create. Let's make this totally concrete with an example. Check out the graph of this function, f of x equals x squared plus 1. It makes this classic U-shape, which we call a parabola. Now, what's so cool here is how the picture tells the whole story. Notice how it stretches out to the sides forever, but it never, ever dips below a certain point. So here's the payoff. You can plug any number on the number line into this function. Positive, negative, you name it. That's its domain. But what comes out? That's the range. And no matter what you put in, the graph clearly shows us the output will always be a number that is 1 or greater. It has a floor that it just can't break through.
Finally, let's talk about that model number you see on the side of the machine, the notation. You're going to see this f of x thing, written f parentheses x, all the time. Don't let it scare you. F is just the name of our function. X is the input. And the whole thing, f of x, just stands for the final output. It's just a modern, more specific way of writing y.
But here's where it gets really, really interesting. Functions aren't static, fixed machines. They're more like Legos. You can take a basic, standard model and start clicking on modifications to build something entirely new, something powerful.
So let's grab a basic piece from our kit. This is our parent function, f of x equals x cubed. Think of this classic S-curve as our standard, off-the-shelf part. Now let's see how we can customize this thing.
We've got 3 basic modifications or transformations we can play with. We can shift the whole graph around, up, down, left, right. We can stretch it taller or compress it flatter. And we can reflect it, basically flipping it into a mirror image.
And by mixing and matching these simple moves, we can create a completely customized function. Look here, we've taken our original x cubed curve, we nudged it 2 units to the right, we squashed it vertically just a little bit, and then we dropped the whole thing down by 1 unit. And just like that, we've built a custom machine from a standard part.
Now that we know we can build with these things, let's take a quick tour through a gallery of the most famous and important functions you'll ever meet. Think of these as the mathematical masterpieces that show up, well, everywhere.
First up, the straight line, the linear function.
It is the definition of steady and predictable. This is the function for anything that changes at a constant rate. Think a car on cruise control, or the simple interest on a loan. If it's a straight shot, it's a linear function.
Next, the parabola, the quadratic function. This is the superstar behind the perfect arc of that basketball shot, or the stream of water from a fountain. It's the signature curve of gravity itself, describing the path of pretty much any object flying through the air.
And here we've got the growth curve, the exponential function. This is the engine of explosive change. It's the curve that shows how compound interest can make a small investment massive, or how a single video goes viral and reaches millions overnight. When things really take off, they follow this path.
Finally, the wave, the sine function. This elegant, repeating wave is kind of like the rhythmic pulse of the universe. It's the function that describes the cycles all around us, from the vibrations of a guitar string making sound to the waves of light that let us see, all the way to the rise and fall of the tides.
So we've met the family, we know how they're built, but this all leads to the big question. Why should you care about any of this outside of a math class? And the answer is actually really simple. Because functions are, quite literally, everywhere.
No, I'm serious. This isn't just theory. This is the toolkit we use to build the modern world. Epidemiologists use functions to predict and control how diseases spread. Animators use them to make the characters in movies move so realistically. They're at the core of weather prediction, they're the blueprint for bridges and skyscrapers, and yeah, they're the engine driving financial markets. They are the secret sauce.
So, the bottom line is this. Functions are way more than just math problems. They represent a huge leap in how we think, the moment we realized we could actually write down the rules of reality in a universal language. They give us the power not just to watch the world, but to model it, predict it, and create within it. And that leaves us with one final, really exciting question. Functions describe the rules of our world. So what new rules are we yet to discover?